Imagine a universe suspended in absolute silence. No stars, no swirling galaxies, no drifting dust, not even the faintest whisper of light. A darkness so complete it feels ancient yet timeless. In this void you sense something looming, a question as old as human curiosity itself. Did the universe truly begin with the Big Bang, or is that just the first page we've managed to read? For a century we have lived under the warm glow of a familiar story, that everything, space, time, matter, energy, erupted from a single, unimaginable instant billions of years ago. A beginning so violent, so luminous, that it shaped the destiny of every star and every life form that would ever emerge. But what if that moment wasn't truly the beginning? What if the Big Bang was not a creation event, but a transition? One chapter in a cosmic tale far older and far stranger than we dare imagine. Picture the earliest scene science allows us to visualize: a blazing ocean of energy hotter than any furnace, denser than any star's core. A storm of particles burst into existence like sparks flying from some unknown forge. Space stretched wildly, expanding faster than any explosion humanity could ever conceive. The universe grew from the size of a subatomic particle to a vast cosmic bubble in a fraction of a second. This image is iconic, embedded in textbooks, documentaries, and the imagination of anyone who has ever wondered how it all began. But before we accept this fiery moment as the absolute start, the camera pulls back. The frame widens. Something feels off, too simple, too neat. The universe, after all, has never been simple. So we pose the forbidden question, one that echoes quietly through the corridors of modern physics. What came before the Big Bang? For decades, scientists avoided this question with an almost philosophical fear. The standard answer was that the question itself was meaningless. There was no before, because time did not exist prior to the event. Asking what came before time was like asking what lies north of the North Pole. A clever response, perhaps, but is it true? Or was it merely a shield built to protect a theory that seemed too elegant to question? The silence of that pre-Big Bang void begins to feel less like emptiness and more like a curtain. And curtains in stories like this are meant to be pulled aside. As you drift through this imagined darkness, you begin to sense motion, not the motion of objects but the motion of ideas. Theories swirl like faint glimmers in the void. Loop quantum cosmology, cyclic universes, conformal time, eternal inflation. Each of them whispers a possibility that the universe may have had a past. A long, complicated, hidden past. A past where space collapsed and rebounded. A past where universes were born and died in an endless cosmic rhythm. A past where time itself might have flowed differently or perhaps not at all. The old certainty begins to crack. You're no longer looking at the Big Bang as a moment of creation, but as a horizon, like standing on the shore of a vast cosmic ocean, realizing the waters stretch far beyond what your eyes can see. That shimmering boundary, once thought to be the beginning, now feels more like a veil concealing a deeper history. And in that realization, a strange feeling emerges. A mix of awe, fear, and an aching curiosity. Because if the Big Bang wasn't truly the start, then everything we thought we knew about our cosmic origins becomes uncertain. Every assumption becomes fragile. And the universe becomes infinitely more mysterious than we imagined. You see flashes, visions of possibilities. A universe collapsing into unimaginable density before erupting outward again like a cosmic heartbeat. A multiverse of countless universes butting off each other like foam on an infinite sea. A primordial state where time is frozen, where the fabric of reality vibrates with potential but nothing yet unfolds. A world before worlds, silent but pregnant with the possibility of existence. These images are not fantasy, they are the forefront of genuine scientific thought. Ideas debated by physicists who stare into equations that stretch the limits of understanding. Researchers who confront anomalies in cosmic data that refuse to fit the old narrative. Scientists who suspect that the universe is trying to tell us something, that the Big Bang is not a beginning but a clue. The void around you becomes alive with questions. What mechanism could trigger a universe? What physical laws could operate before classical time? Is the universe eternal, cyclic, emergent, or part of a larger structure where beginnings and endings lose meaning? Every question only deepens the mystery. The comforting story of a single definitive beginning dissolves, replaced by something more overwhelming. A universe that may have existed before the Big Bang, perhaps for eternity. A universe shaped by processes we're only beginning to glimpse. A universe where our cosmic origin is not a singular event, but a chapter in a saga far beyond human comprehension. And yet, within that uncertainty lies a strange beauty. Because the unknown is not a void to fear, it is an invitation. An invitation to keep looking, keep questioning, keep imagining. To realize that our universe, vast and ancient as it is, may still be in its opening scenes. The silence returns, but now it feels different. Not empty but expectant. As if the universe itself is holding its breath, waiting for us to ask the next question. What if the Big Bang was not the dawn of everything, but simply the moment we gained a window into a far older reality? The journey begins with that unsettling, electrifying thought. And once you feel it, there is no turning back. For most of us, the story of the universe begins with a single, dazzling instant. A moment compressed into a sentence so familiar it almost feels comforting. The universe began with the Big Bang. It's a phrase repeated in classrooms, whispered in planetariums, and echoed across scientific documentaries for generations. Even people who know little about physics know this story, because it feels like the closest thing we have to a creation myth rooted in science, not legend. But as we move deeper into the narrative, something becomes clear. What we think we know about the Big Bang is built on a few powerful images stitched together over decades. These images feel real, almost cinematic, but they are, in many ways, interpretations. Human interpretations. Simplifications of a cosmic event so extreme it defies imagination. Picture this familiar beginning. An impossibly tiny point of infinite density, a singularity, suddenly erupting in a furious burst of energy. Light floods into existence. Particles form in a storm of heat and pressure. Space itself stretches outward, expanding faster than light. In seconds, the universe grows from subatomic to astronomical. This is the version most of us grew up with. A universe emerging violently from nothing. Yet the more you stare at this picture, the more it begins to tremble at the edges. This traditional story was shaped in the mid-20th century, during a period of scientific triumph. Observations by Edwin Hubble revealed that galaxies were racing away from one another, suggesting that space was expanding. Later, the discovery of the cosmic microwave background seemed like an afterglow of that first fiery moment. A photograph of the universe when it was only 380,000 years old. For decades, these clues pointed toward a powerful conclusion. Everything must have once been compressed into a single point. It was simple. It was elegant. And it was accepted. But that simplicity is also the first hint that something might be missing. The universe, after all, rarely offers simplicity. Nature hides complexity in every corner, from the quantum world to the vast web of galaxies. Why should the beginning of everything be any different? Imagine standing in a dark theater as the opening scene begins. The screen flashes with light, sound, and motion, but you know instinctively that the story did not begin at that instant. Something happened before the scene you see. Characters lived, choices were made, worlds formed. You're only witnessing the moment where your perspective enters. What if the Big Bang is not the first scene of the universe, but simply the first one we can observe? Science, as powerful as it is, reaches a wall at the earliest moments of the Big Bang. Our equations fail as time approaches zero. Our understanding collapses. And beyond that wall, we are blind. This blindness is not a limitation of imagination. It is a limitation of the physics we currently have. And so, when we say, the universe began with the Big Bang, what we often mean is, our understanding begins with the Big Bang. The distinction is subtle but profound. Still, the traditional story persists because the evidence supporting it is solid, at least for everything that happened after the first tiny fraction of a second. We can trace the expansion of the cosmos. We can detect the fading radiation that bathes all of space. We can see the large-scale structure of galaxies forming over billions of years. All of it aligns beautifully with the Big Bang model. But the moment we rewind the cosmic clock to the very beginning, to the part of the story where everything is supposed to start, it is like approaching a horizon that keeps receding. The closer we get, the more distorted our understanding becomes. Imagine trying to watch an old film reel, only to discover the first few frames have been burned away. What you see begins suddenly, abruptly, without explanation. You can infer what may have happened before, but the images are gone, forever out of reach. That missing footage is the mystery at the heart of cosmology. And yet, despite these gaps, the standard Big Bang story still holds enormous emotional power. There is something deeply human about wanting a beginning. A first moment. A birthplace for everything. It aligns with our myths, our religions, our instinct that everything that exists must arise from somewhere. The Big Bang fits this need so perfectly that for decades, scientists and the public embraced it as an origin tale, pure and absolute. But slowly the edges of the story began to show seams. The idea of a singularity, an infinitely dense point, may not reflect a real physical state. It may instead be a mathematical placeholder, a sign that our equations stopped working. Some physicists now believe the universe never shrank to a point at all. They propose bouncing universes, collapsing universes, quantum phases, pre-existing structures, and even cosmic fields that stretched across time before the Big Bang. The more we probe the early universe, the more the ground shifts beneath us. As you visualize the Big Bang once more, the brilliant eruption, the newborn particles, the wild expansion, another image begins to flicker behind it. A shadow. A hidden frame. Something that came before, shaping the conditions of that cosmic detonation. Something older than our universe's first second. Perhaps the universe existed in another form. Perhaps space had a previous life. Perhaps time flowed differently, slower, faster, or not at all. These ideas feel almost forbidden, yet they are now at the heart of cutting-edge physics. And so the classic Big Bang story takes on a new tone. It is no longer the unchallenged beginning, but one theory among many, a powerful one but not the final word. The certainty once wrapped around it begins to unravel like an old threadbare fabric. You feel a shift. What was once a neatly packaged origin tale now expands into a vast ocean of possibilities. The familiar narrative was only the surface. Below it lies depth, cold, dark, mysterious, but irresistibly calling. We stand today in a strange position. We know more about the universe than any generation before us, yet the beginning has never felt further away. The deeper we investigate, the more questions we uncover. The moment we thought marked the birth of everything may instead be a door, a threshold into something astonishing. As you drift through these thoughts, the universe seems to grow older, stranger, more enigmatic. The Big Bang is no longer just an explosion. It is a clue, a trace, a signpost that points toward something far more profound than a single moment of creation. And the question that now rises quietly and relentlessly is this: if the Big Bang wasn't the true beginning, then what cosmic story lies hidden beyond that first flash of light? When we trace the universe backward through time, peeling away billions of years like layers of cosmic sediment, we eventually reach a point where all roads converge, the evidence that built the foundation of the Big Bang story. These clues are ancient, older than every star, older than every galaxy, older than the very atoms that compose our bodies. They form the pillars of a theory that has shaped the way humanity imagines its origins. And yet, even these pillars, as solid as they seem, whisper complexities that we often overlook. The first great clue reveals itself in the motion of galaxies. Imagine standing in the center of the universe, though no such center truly exists, and watching every galaxy drift away, pulled by a mysterious expansion. Their light stretches as they recede, reddening like embers cooling in the night. This redshift is not merely a visual effect. It is a cosmic message, a signature etched into the fabric of space-time. It tells us that the universe is not static but stretching like an enormous cosmic canvas. This expansion implies something profound. If galaxies are moving apart now, they must have once been closer, so close they filled a single, compact space. The second clue glows softly across the universe like a forgotten relic, the cosmic microwave background. Picture it as a faint, ancient whisper of heat that lingers everywhere, in every direction, an echo from a time when the universe was young and burning bright. This radiation is not a beam or a ray, it is a bath of gentle warmth spread evenly across the cosmos, like the last fading embers of a great fire. It is the afterglow of the early universe, frozen in time. When scientists first detected it, they realized they were listening to the universe's oldest memory, a snapshot of a moment only 380,000 years after the Big Bang. In that ancient picture, we see tiny fluctuations, small variations in temperature scattered across the sky. These subtle ripples, barely detectable, would later seed the formation of galaxies, clusters, and cosmic structure. They are like the universe's first fingerprints, delicate but enduring. Without them, nothing solid would have formed. No stars, no planets, no life. A third piece of evidence comes from the very elements that form the universe. Hydrogen, helium, and lithium, the simplest elements, exist in extremely precise ratios across all space. Those ratios are not random. They are the chemical signature of primordial nucleosynthesis, the process by which the first atomic nuclei took shape in the fiery seconds after the universe began. It's as if the early cosmos forged these elements in a brief moment of furious creation, leaving behind a recipe that still permeates the universe today. These three clues, expansion, ancient light, and elemental abundance, fit together like parts of a grand puzzle. They reinforce the story that the universe was once hot, dense, and rapidly growing. They point back toward a single conclusion that defined modern cosmology: there was a beginning. For decades, this evidence felt unshakable. It was elegant, consistent, and powerful. When stitched together, it formed an image so compelling that it became the accepted cosmic origin story for nearly a century. But as you contemplate these clues once more, something subtle begins to shift. The redshift tells us galaxies are moving apart, but it does not prove they came from a singular point. Expansion could have started from many different states, not necessarily a true beginning. The afterglow of cosmic radiation is ancient, yes, but it begins hundreds of thousands of years after the presumed bang. It is not a photograph of the beginning itself, only a record of what came after. And the elemental abundance, while remarkable, tells us the universe was once hot and dense, but not necessarily how that state came to be. The evidence is real. The interpretations, however, are human. You begin to feel the edges of uncertainty. What once seemed like hard proof now feels more like the outline of a deeper truth, an impression, not a direct image. Each piece of evidence describes the universe as it was long after the bang, not at the moment it began. Our cosmic clues are shadows cast by ancient processes, not direct windows into the birth of time. It's like reconstructing the opening lines of a book after missing the first few pages. You might piece together the plot, infer the characters, guess the themes, but you cannot know for sure what the true beginning looked like. The cosmic microwave background may be an echo, but every echo comes from something. What produced that first sound? What rang through the newborn universe? What force or process ignited the heat that still glows today? These questions pull at the edges of the evidence. They do not undermine it, they challenge us to see beyond it. The camera pulls back, revealing that our cosmic clues are not endpoints but gateways. Each one opens into deeper mysteries. Why is the afterglow so uniform? Why did the universe expand so smoothly? Why do the smallest temperature fluctuations match patterns predicted by quantum processes? The evidence that once seemed complete suddenly feels incomplete, not wrong, simply unfinished. Like fragments of a much larger, more intricate narrative. And as you step back and look once more at these clues, the stretching galaxies, the ancient radiation, the primordial elements, you begin to sense a quiet truth. The evidence does not confine us to one explanation. It invites us to look deeper, to ask what forces shaped these earliest moments, what physics lies behind the cosmic curtain. The universe leaves breadcrumbs, not answers. And every clue, no matter how ancient, whispers the same haunting implication. The story may not have started where we think it did. For decades, the Big Bang stood like an unshakable monument at the center of cosmology. A story so coherent, so beautifully aligned with observations, that questioning it felt almost heretical. Yet science advances not through comfort but through contradictions. And in the shadows of the familiar narrative, small cracks began to appear, tiny fractures in the cosmic origin story that refused to be ignored. Each one subtle at first, but together forming a pattern that whispered of something deeper, something concealed just beyond the boundaries of our understanding. Imagine the universe as a vast mural painted across the sky. From a distance the artwork looks flawless. But when you step closer, examining the fine details, you notice imperfections, brushstrokes that don't align, colors that seem slightly out of place, shadows that hint at scenes beneath the surface. These are the anomalies that haunt the Big Bang model. And they have grown too numerous, too precise, too persistent to dismiss as mere noise. One of the earliest cracks emerged from the universe's astonishing uniformity. The cosmic microwave background, the ancient afterglow of the early universe, appears remarkably smooth. The temperature difference from one part of the sky to another is so small, so shockingly consistent, that it defies the logic of a universe that once consisted of rapidly spreading, disconnected regions. How could patches of space that were never in contact share the same temperature? There wasn't enough time for light, or heat, to travel between them. It was as if the universe coordinated its initial conditions with impossible precision. Scientists called this the horizon problem. A problem that the standard Big Bang alone could not solve. Then came the flatness problem. When physicists measured the geometry of the universe, they discovered it was astonishingly flat. Not curved like a sphere, not warped like a saddle, just flat. Perfectly, exquisitely flat. But flatness is unstable. Any slight deviation in the early universe would have grown dramatically over billions of years. The fact that it remains flat today suggests that the early universe was fine-tuned to unimaginable precision. What? Oh. Each of these issues whispered the same unsettling implication. The universe's initial state was too perfect, too coordinated, too delicately balanced for the Big Bang to explain on its own. Other cracks emerged from unexpected corners of the universe, regions where galaxies clumped together in ways that defied predictions. Strange alignments in the cosmic microwave background formed eerie patterns known as the axis of evil, a large-scale asymmetry that seemed out of place in an otherwise uniform cosmos. Some physicists dismissed it as a statistical fluke. Others saw in it the faint outline of a deeper cosmic structure, perhaps rooted in a time before the Big Bang. There were anomalies in galaxy rotation curves, in the behavior of dark matter, in the distribution of large-scale cosmic structures spanning hundreds of millions of light-years. Each anomaly opened a new doorway of doubt. Each doorway revealed a small corridor of possibility leading away from the familiar model. And then came the mystery of cosmic inflation, a theoretical patch introduced to save the Big Bang from its growing list of inconsistencies. Inflation was bold, elegant, and useful. It proposed that the universe expanded exponentially in the tiniest fraction of a second after the Big Bang, smoothing out the horizon and flattening space. It explained the uniformity. It explained the flatness. It explained the structure of the cosmic microwave background. But inflation came with its own cracks so large they threatened to overshadow the ones it was meant to fix. To make inflation work, physicists had to invoke hypothetical fields with finely tuned properties, fields we have never detected. The timing had to be extraordinarily precise. Inflation had to start at exactly the right moment and end at exactly the right moment. Too short and the universe would still be uneven. Too long and galaxies would never form. And even if the timing was perfect, the mechanism that started inflation, and the mechanism that stopped it, remained complete mysteries. It was like finding a key that fit the lock perfectly, only to realize you have no idea who made the key, where it came from, or why it works. As these cracks accumulated, scientists began to confront an uncomfortable possibility. The Big Bang, while powerful, might not be the full story. It explained what happened after the first fraction of a second with exquisite clarity, but it remained silent on what triggered the event. Silent on the conditions that made it possible. Silent on the forces that shaped the earliest moments of existence. And so the scientific community started probing deeper, exploring data with new instruments, new telescopes, new algorithms. They examined gravitational waves, cosmic microwave background polarization, quantum fluctuations frozen across the sky. And in these deeper observations, whispers of something older and more enigmatic began to emerge. Fluctuations in the cosmic microwave background seemed to hint at non-random patterns, echoes that did not belong to a simple expanding universe. Some simulations suggested that the universe might carry imprints of a preceding contraction. Others hinted at physics that could operate before classical time. Still others showed anomalies so subtle that they could only be explained by processes occurring before the Big Bang itself. The old story trembled. It wasn't just data that fueled the unease. Theoretical physics also began to revolt. Equations describing quantum gravity, attempts to merge general relativity and quantum mechanics, refused to produce a singularity. The mathematics simply didn't allow the universe to shrink to a literal point of infinite density. Instead, the equations suggested a bounce or a boundary or a transition. Anything but a true beginning. It was as if the universe itself was resisting the idea of a singular start. Cosmologists found themselves facing a profound shift. The Big Bang still described the early universe beautifully, but only from a certain frame onward. Before that frame, the story grew blurry, fragmented, incomplete. Like a film whose first reel had been lost, leaving us with a beginning that wasn't truly the beginning. A deeper question emerged, one that grew louder with every anomaly. What lies behind the cosmic cracks? Is the universe trying to reveal a hidden chapter? Are these anomalies clues, breadcrumbs leading us backward in time? Or are they warnings that our current theories are missing something fundamental, something buried in the physics of the earliest moments? The cracks do not break the Big Bang, they illuminate its limits. They reveal the edges of the map, where the familiar world ends and the unknown begins. They invite us to peer past the comforting story we've repeated for a century and ask a question that feels both thrilling and terrifying. If the Big Bang isn't the whole origin story, then what cosmic truth lies beyond the veil of our earliest light? The cracks widen, not to destroy the narrative, but to guide us toward the next chapter. A chapter written not in certainty but in mystery. For most of scientific history, asking what existed before the Big Bang was treated not just as a difficult question, but as a forbidden one. A question that broke the rules. A question that seemed, at least to the scientific establishment, not only unanswerable but fundamentally meaningless. Time, we were told, began at the Big Bang. Space began at the Big Bang. Cause and effect began at the Big Bang. To ask what came before was to step outside the boundaries of physics and into the realm of metaphysics, myth, or imagination. Yet the human mind has never been satisfied with boundaries. Curiosity pushes forward the moment someone says, "This far, no further." And so, despite decades of scientific restraint, a whisper lingered beneath the surface. A quiet defiance shared by philosophers, cosmologists, and dreamers alike. What if there was something before? Picture a world where scholars, for centuries, believed Earth was the center of the universe. Their reasoning seemed airtight, grounded in observation and tradition. But then a single question, what if we're not the center? Shattered the cosmic map. The same pattern repeats throughout human history. Every time we declare something unknowable, the universe eventually forces us to confront it. The origins of the Big Bang taboo stretch back to the very equations that built modern cosmology. Einstein's general relativity describes gravity as the curvature of spacetime. When physicists applied those equations backward in time, the universe seemed to shrink, compressing into an infinitesimal point. A singularity where density becomes infinite and the laws of physics break down. At that moment, all the machinery of science fails. Mathematics dissolves. Predictability collapses. Faced with this collapse, early cosmologists made a choice. Rather than admit ignorance, they declared the question invalid. If time itself begins at the Big Bang, then the phrase "before the Big Bang" describes a state without time, and therefore, by their reasoning, nothing meaningful could exist there. But silence is not the same as certainty. 4,000s of years before scientific cosmology matured, ancient civilizations crafted their own answers to the question of before. The Egyptians imagined a vast, dark ocean called Nun from which creation emerged. The Greeks spoke of chaos, an infinite void preceding the ordered cosmos. Hindu cosmology envisioned endless cycles of creation and destruction, universes being born, dying, and being reborn in eternal rhythms. Even the Maya imagined time not as a straight line but as a loop. Though we now recognize these myths as symbolic, their one shared feature remains striking. Almost none of them describe the universe as having a single, absolute beginning. They envision cycles, transitions, cosmic breaths. As you reflect on these ancient stories, something becomes clear. They may not have possessed the tools of modern science, but they instinctively sensed something modern cosmology is only now beginning to reconsider: that the universe might have a past. For centuries, the scientific taboo tried to silence this instinct. The early Big Bang model, elegant and exhilarating, carried the implicit promise of finality. A clear beginning. A moment that needed no earlier context. Many scientists liked this idea because it made cosmology feel clean, complete, comprehensible. And yet, the universe resisted this simplicity. As observations improved and telescopes grew more powerful, the earliest moments of the universe began to feel less like a creation event and more like a transition. The singularity, a mathematical ghost, began to fade from serious theory. Quantum mechanics refused to allow infinite density. The horizon and flatness problems demanded a deeper explanation. Inflation patched some cracks but opened others. Slowly, inevitably, the scientific taboo began to unravel. And once the taboo weakened, the forbidden question returned with new force. Physicists began to imagine scenarios where the universe did not begin, but transformed. Some models proposed that a previous universe collapsed into a dense quantum state before bouncing outward again. Others suggested that time might extend infinitely into the past, but the early era looked nothing like the universe we know. Still others imagined a timeless phase, where quantum fluctuations existed without direction or order, only to burst into classical time through a transition we misinterpreted as a beginning. These were no longer metaphysical speculations. They were testable scientific ideas supported by equations, simulations, and data-driven predictions. But the psychological barrier remained. Asking what came before forces us to confront unsettling possibilities. If the Big Bang wasn't the first moment, then the comforting illusion of a definitive beginning disappears. Humanity loses the privilege of standing at the dawn of existence. Instead, we become part of a much larger, older, perhaps eternal story whose full scope we may never fully grasp. And yet, the forbidden question persists, because within it lies the deepest mystery of all. Imagine standing at the edge of a cliff looking into a fog-covered valley. For years, you were told that beyond the fog lies nothingness, a sheer drop into emptiness. But then, faint shapes begin to emerge in the mist, outlines of mountains, the shimmer of water, the suggestion of landscapes stretching beyond sight. The belief in nothingness begins to crumble. The universe is revealing traces of a prelude. Hints in the cosmic microwave background suggest patterns imprinted before the Big Bang. The mathematics of quantum gravity refuses to allow the singularity. Cyclic models predict signatures that researchers are beginning to search for in the sky. Some cosmologists even propose that black holes might generate new universes, hinting at a cosmic lineage stretching across unimaginable epochs. The forbidden question suddenly feels less like a boundary and more like a doorway. You begin to realize that the taboo was never scientific. It was emotional. It existed because the idea of a universe with no beginning feels overwhelming, almost existentially frightening. The human mind prefers clean stories, tidy arcs, defined origins. But the cosmos is under no obligation to be emotionally convenient. Instead, it confronts us with something far grander. As the ancient myths suggested, as modern theories now propose, and as the data begins to hint, the universe may not have emerged from nothing. It may have flowed from something, transformed from something, or cycled through states we cannot yet fully imagine. And once that possibility sinks in, a quiet exhilaration takes hold. Because the question, what came before, is not a challenge to our understanding. It is an invitation. An invitation to expand the boundaries of science. An invitation to rethink the nature of time. An invitation to imagine a universe that did not simply begin but evolved. The forbidden question is no longer forbidden. It is the next step, the pivot point where curiosity overtakes caution, where mystery becomes momentum. And in that moment you sense the strange, humbling truth. The Big Bang may be the earliest moment we can currently see, but it may not be the first moment the universe ever lived. The curtain is lifting, and behind it, the cosmos is older, deeper, and more mysterious than we ever dared to believe. For a moment, imagine the early universe as a turbulent sea, violent, chaotic, and expanding with a speed that defies all sense. In this sea, one idea rose like a towering wave, promising to calm the chaos and explain the mysteries buried in the earliest fraction of a second: cosmic inflation. It was bold. It was elegant. It was the answer everyone had been searching for. But as the decades passed, this answer began to tremble. Inflation, once celebrated as the great unifying fix, started to reveal deep, unsettling flaws, cracks that hinted at something fundamentally unstable beneath its surface. To understand the problem, picture the universe just after the Big Bang. According to the original theory, the dense, hot fireball should have produced a cosmos that was wildly uneven. Patches of extreme heat next to patches of extreme cold, regions of intense density bordering regions of emptiness. Chaos should have ruled. But the universe we observe today is astonishingly smooth. No matter where we point our telescopes, the temperature of the cosmic microwave background is nearly identical, varying only by tiny fractions of a degree. Inflation seemed to solve this beautifully. It proposed that the universe expanded exponentially in an unimaginably small slice of time, far faster than any conventional process could allow. This rapid stretching would have smoothed out all irregularities, ironing the universe into the nearly uniform state we now see. It was like taking a crumpled piece of paper and pulling it so quickly and so forcefully that all the wrinkles flattened instantly. For a while the idea felt perfect. Inflation explained why distant regions of the universe look identical even though they were never close enough to exchange light or heat. It explained the flatness problem, giving us a universe balanced with astonishing precision. It even predicted certain patterns in the cosmic microwave background that were later observed. It was clever. It was powerful. It was satisfying. But behind this elegant solution lurked a troubling truth. The theory required assumptions so precise, so finely tuned, that they began to feel unnatural. Inflation needed a mysterious entity called the inflaton field, a hypothetical form of energy that could drive the universe apart at faster-than-light rates. But no one has ever detected such a field. No particle physics experiment has hinted at its existence. Its properties had to be set just right: its strength, its decay rate, its potential energy curve. Everything had to be perfect. Too strong, and the universe would have torn itself into sterile emptiness. Too weak, and the cosmos would have collapsed back into chaos. Even the timing had to be exact. Inflation needed to turn on at precisely the right moment, run for precisely the right duration, and then switch off with extraordinary delicacy. If it ended too early, the universe would be misshapen. If it ended too late, galaxies could never form. It was like discovering a bridge spanning a vast canyon, beautiful and useful, but realizing every beam, bolt, and cable was required to be aligned with impossible precision. One fraction of a millimeter off, and the entire structure would collapse. Over time, physicists began to notice even deeper cracks. The mathematics of inflation suggested that, once started, inflation might not stop everywhere. Instead, in many simulations it continued eternally in various regions of space, creating countless bubble universes, each one expanding, splitting, and spawning new universes in an endless fractal cascade. This idea, called eternal inflation, was breathtaking but deeply unsettling. It turned our universe into just one bubble among an infinite cosmic foam. The theory that was meant to explain our universe instead predicted a vast multiverse, an infinite collection of universes with different physical laws. And if anything is possible somewhere in the multiverse, how can we use inflation to explain the universe we actually see? Inflation began to feel less like a single solution and more like a machine that produced every possible outcome. A theory that could explain anything explains nothing. Some scientists proposed modifications, crafting more exotic inflatant potentials, tweaking equations, or adding new fields and forces. But each adjustment felt less like discovery and more like desperation. A patch on top of a patch, like a tapestry stitched with increasingly tangled threads. As observations sharpened, the problems grew sharper too. Satellite missions that mapped the cosmic microwave background revealed inconsistencies the simplest inflation models could not explain. The predicted patterns of primordial gravitational waves, once expected to be inflation's smoking gun, failed to appear. Some versions of inflation were ruled out entirely. Others became increasingly implausible. Inflation, once the cosmic hero, now seemed unstable, uncertain, and incomplete. Even its creator, physicist Alan Guth, acknowledged that inflation might not be the final answer. Prominent scientists like Paul Steinhardt, one of inflation's early developers, became some of its strongest critics, arguing that inflation predicted too many universes and not enough certainty. Slowly, a new question surfaced, a question that felt like a quiet rebellion. Was inflation a temporary fix, not a true solution? Perhaps it was a bridge, helpful but not the right structure to support the ultimate truth of the cosmos. Maybe inflation works, but only as an approximation. Or maybe it hints at a deeper process, a mechanism from a previous universe, a quantum transition, a bounce, or something so unfamiliar that our equations barely grasp its outline. As you watch inflation unravel, the scene shifts. What once appeared to be a solid pillar of cosmology now looks more like scaffolding, temporary, fragile, and built around a mystery far older than the Big Bang. The cracks in inflation do not destroy the story. They illuminate the next question, the next doorway, the next frontier. Because if inflation is not the final answer, then something else shaped the universe's earliest moments. Something more fundamental, more elegant, and perhaps more ancient. And behind that possibility lies a profound realization. The universe may not just be expanding. It may be revealing the truth, piece by piece, about what really came before. Imagine the universe not as a singular beginning, but as a rhythmic breath, an eternal cycle of contraction and expansion, collapse and rebirth. This idea, once dismissed as poetic speculation, has emerged again at the forefront of theoretical physics under a new scientific framework, loop quantum cosmology. And within its equations lies one of the most audacious possibilities ever proposed about our cosmic origins, that the universe did not begin with a bang at all, but with a bounce. Picture the universe in its final moments before the Big Bang era as we know it. Space is collapsing in on itself, galaxies spiraling closer, stars crushed into one another by increasing gravitational pressure. The cosmos shrinks, compressing all matter, energy, and spacetime into a state of unimaginable density, but not into a singularity. Instead, as the universe approaches an incredibly small volume, quantum effects awaken. They ignite like sparks in the dark, rewriting the rules of gravity and preventing the collapse from reaching infinity. This is where loop quantum cosmology reveals its power. It suggests that spacetime is not continuous but made of tiny, discrete units, like the pixels of a digital image or the grains of sand on a beach. These units are so small that they evade detection in everyday physics, but in extreme conditions such as near the supposed singularity, they dominate the behavior of the universe. They generate a repulsive force that counters gravity exactly at the moment collapse would otherwise become catastrophic. Instead of a dead-end singularity, the universe hits a quantum floor. And from that floor it rebounds, a cosmic bounce. Envision that moment. In the final heartbeat of the collapsing universe, spacetime becomes tightly woven, its fabric pulled to its limit. The compression reaches a threshold where gravity, instead of pulling inward uncontrollably, flips into a new regime. It becomes repulsive. It pushes outward. The imploding cosmos halts for an instant, silent, motionless, suspended in a state beyond ordinary time. Then everything erupts. The rebound triggers an expansion not from nothing but from a previous cosmic phase. The universe begins to grow, accelerating outward, igniting the chain of events that mimic what we call the Big Bang. In this view, the Big Bang is not a beginning but a bridge, one side collapsing, the other rising. Imagine this cycle repeating endlessly. A universe that collapses into itself, reaches a quantum limit and bounces back outward. Over trillions of years, it expands, forms stars and galaxies, disperses, cools, and eventually falls back toward contraction, only to rebound once more. An eternal dance. A cosmic heartbeat. This vision transforms the entire narrative of existence. The universe is no longer a fragile miracle born from an inexplicable moment but a natural process unfolding across infinite epochs. Everything that exists now may be a faint echo of a previous universe. And everything that will exist in the far future may be shaped by the remnants of our own. Loop quantum cosmology gives mathematical structure to this idea. It builds upon the framework of loop quantum gravity, a theory that attempts to reconcile general relativity with quantum mechanics by quantizing spacetime itself. In this theory, spacetime is not a smooth stage but a woven lattice of loops. These loops govern the geometry of everything from black holes to the cosmos itself. At ordinary scales, the loops are too small to detect. But at the brink of cosmic collapse, they become dominant. They prevent infinite density by providing an absolute minimum size to the fabric of space. Gravity cannot crush spacetime beyond that limit. The universe cannot collapse into a singularity. The bounce is therefore not just a metaphor, it is a physical transition predicted by the mathematics. Imagine watching that transition unfold. In the contracting universe, galaxies collide and vanish into a dense ocean of radiation. Temperatures rise beyond imagination, matter disintegrates and spacetime ripples violently. Yet as the compression intensifies, the quantum geometry of space begins to shimmer, resisting collapse. The universe shrinks to a size far smaller than an atom and then, a moment of pure stillness. A silence so absolute it feels eternal. Then the bounce cascades outward, igniting a shockwave of creation. Space stretches. Energy bursts into motion. Particles form in a storm of quantum fluctuations. Light emerges. Heat spreads. The early universe becomes a cauldron of fire and plasma, fluid, glowing, alive. This is the moment we traditionally call the Big Bang. But now you see it differently, not a creation ex nihilo but a transformation. Not a beginning but a turning point. This perspective raises profound questions. If each bounce carries information from the previous universe, what relics of past cycles might still linger in our cosmos today? Could patterns in the cosmic microwave background, those faint ancient ripples, carry subtle imprints left behind by a universe before ours? Could anomalies in the universe's structure be remnants of events that occurred not billions but trillions of years ago? Physicists are beginning to look for these clues. Some models predict that certain features, such as particular shapes in the temperature fluctuations of the cosmic microwave background, might reveal traces of a preceding contraction. Others suggest that unexpected alignments or asymmetries in the cosmic map could be fingerprints of a bounce. If any of these patterns are confirmed, they would reveal something extraordinary. Our universe carries memories. The emotional impact of this idea is breathtaking. It transforms our relationship with existence from a brief spark in a random explosion to a verse in an ancient cosmic poem. We become participants in a story older than time as we know it. A story that has unfolded countless times and will continue long after our universe fades into darkness. Yet the bounce hypothesis also brings with it a sense of fragility. If the universe will one day collapse again, then everything we know, every galaxy, every star, every planet, every atom, will eventually fall back into the cosmic furnace. The beauty we see today is temporary, fleeting, part of a grand cycle beyond our control. But paradoxically, this fragility brings comfort. For if the universe has died before and been reborn, then cosmic endings are not final. They are transitions. No cycle is wasted. No universe is truly lost. The bounce becomes a metaphor not just for cosmology but for existence itself. In this new vision, the Big Bang is not a lone miracle. It is a stage in an endless rhythm. A rising breath after a cosmic exhale. A spark in an infinite sequence of creation, collapse, and renewal. And the question lingering at the edge of this idea is as haunting as it is exhilarating. If our universe is the result of a bounce, then what stories were written in the cosmos that came before us? And what stories will unfold in the universe that follows? Imagine standing at the edge of existence, watching the universe inhale and exhale across unimaginable stretches of time. Galaxies bloom, burn, fade, and collapse. Space stretches and then contracts. Light cuts across the cosmic dark, only to be swallowed again by the growing pull of gravity. This is not a universe with a single beginning or a single destiny. This is a universe woven into a tapestry of eternal cycles, each one rising from the ashes of the last. This idea, known as the cyclic model, confronts the comforting simplicity of the Big Bang narrative and replaces it with a far older, more intricate story. A story where the universe does not begin, it flows. It pulses. It transitions from one cosmic phase to another like the heartbeat of an ancient, living entity. Picture a single cycle. At first, the universe expands, galaxies drifting apart like lanterns carried by a gentle tide. Stars ignite and explode. Black holes grow heavy with the matter they consume. Over trillions of years, the expansion slows as gravity begins to pull everything back inward. The universe cools. Light dims. The cosmic web tightens. And slowly, inevitably, everything folds back into itself. Then comes a moment of immense pressure and density. A moment where the universe, compressed into a near-uniform state, reaches a critical threshold. Instead of collapsing into a singularity, it transitions. It shifts into a new state, and from that state, a new cosmic expansion begins. A new cycle. A new universe. This vision carries a profound emotional duality, a mixture of awe at the grandeur of eternal creation and fear at the fragility of each individual cycle. It suggests that everything we know, our galaxies, our stars, our worlds, is just one act in an infinite cosmic drama, destined to fade but also destined to be followed by countless new beginnings. The idea of a cyclic universe is not new. Ancient cultures across the world imagine time as a wheel, not a line. The Hindu concept of the Mahayuga describes endless cycles of creation and destruction. The Stoics believed in cosmic conflagrations followed by rebirth. Even early Buddhist cosmology spoke of universes forming and dissolving like breaths of an eternal force. Modern physics, in some ways, has returned to these ancient intuitions. The cyclic model gained new momentum when physicists realized that certain features of the universe, its smoothness, its flatness, its structure, could be explained without resorting to inflation. Instead of a rapid, sudden expansion, the cyclic model slows the narrative down, revealing a universe guided by long, graceful transitions. The conditions we observe today, according to this idea, were not set in a violent instant but shaped over vast cosmic ages during previous cycles. Imagine a universe collapsing not into chaos but into order. As everything folds inward, irregularities are smoothed out. The cosmos becomes uniform, balanced, and ready for the next beginning. In this picture, the universe is like a master craftsman, refining itself across endless cycles until each new expansion emerges with just the right conditions for galaxies, stars, and life. This vision carries an eerie beauty. It suggests that our universe is not random or lucky. It is the product of countless cosmic eras, sculpted by time itself. But this beauty is matched by a quiet dread. Because if the universe cycles eternally, then all things, every achievement, every civilization, every star, are transient. Nothing lasts forever. Even entire universes are temporary chapters in a story that stretches beyond human meaning. Yet this impermanence is counterbalanced by a strange comfort. For if everything ends, everything also begins again. The death of one universe is the birth of the next. The collapse of cosmic structure is also the planting of cosmic seeds. Every ending is an opening, every contraction a preparation for expansion. In the cyclic view, the Big Bang is not an explosion. It is a rebirth. Some versions of the cyclic model imagine universes that inherit certain features from previous cycles, echoes of past cosmic structures that ripple into the next era. Others propose that each universe starts nearly fresh, with only faint quantum traces of its predecessor. Still others suggest that universes in different cycles may differ dramatically, each with unique physical laws or unique patterns of structure. The diversity of these possibilities only deepens the mystery. If our universe is one in a sequence, then what came before us? Was the previous universe similar or entirely different? Did it contain galaxies like ours? Stars like ours? Life like ours? Did it leave behind imprints that we might detect? Subtle scars in the cosmic microwave background, strange alignments, or statistical anomalies hinting at a deeper history? Some researchers are actively searching for these signatures. They hunt for circular patterns in the cosmic afterglow, patterns that might be echoes of massive events like collisions of black holes, in a universe that existed before ours. They search for asymmetries in the cosmic map, tiny whispers of structure passed down through cycles like inherited memories. These searches are controversial. Some scientists consider the evidence inconclusive. Others argue it could be the beginning of a revelation, a sign that our universe carries ancient imprints, like fossils embedded in the cosmic sky. If such evidence is ever confirmed, it would mean something astonishing, Our universe is not alone, and it is not the first. But even without definitive proof, the cyclic model offers a new way to imagine time itself. Instead of a single arrow moving from a beginning to an end, time becomes a loop. A corridor that circles back on itself. A river with no true starting point. An eternal recurrence of cosmic eras, each one giving way to the next. This vision transforms the emotional tone of the universe. Instead of a cosmos born from a fleeting burst of chance, we enter a universe steeped in ancient rhythms. A universe that breathes. A universe that lives. And yet, at the center of this vision, a question lingers like a shadow. If the universe has cycled through countless phases before ours, how many times has everything we know risen and fallen? How many universes came before and how many will come after? And in that endless sequence, what does it truly mean for a universe to begin, or to end? The cyclic universe stretches our imagination beyond the boundaries of a single creation event and invites us into an endless cosmic story, where every ending is simply the beginning of another chapter waiting to unfold. Imagine looking at the night sky and sensing, just faintly, that something ancient is staring back. Not the stars, not the galaxies, not the cosmic background glow, but something older. Something from a universe that existed before ours. This is the haunting possibility proposed by conformal cyclic cosmology, a theory that imagines time not as a single line, but as a sequence of cosmic eons, each one giving birth to the next. And at the boundary between these eons, the universe leaves behind subtle fingerprints, echoes of worlds long vanished. Picture a universe at the end of its life. Stars have burned out. Black holes have consumed galaxies and then evaporated through Hawking radiation. Matter itself begins to dissolve as particles decay and disappear. What remains is not a universe filled with things, but a universe filled with light, vast, cold, empty but not dead. With no mass left to measure time, the concept of time itself begins to fade. Distances lose meaning. The universe becomes a smooth, featureless sea of radiation, stretching endlessly. Now imagine compressing this late-stage universe, this weightless, timeless ocean, into a new beginning. Not through a violent explosion, but through a conformal transformation, where scale ceases to matter. The infinite future of one universe becomes the fiery birth of the next. The horizon of one aeon becomes the spark of another. In this view, the Big Bang wasn't the beginning. It was a continuation. The idea is almost poetic. The death of one cosmos becomes the birth of another, not through collapse or bounce, but through a transformation of geometry itself. Time continues, but the universe resets. A new aeon dawns, built upon the decayed remains of the previous one, its radiation becoming the seed of new structure. But the most haunting part of this theory isn't its elegance. It's that it predicts evidence. Evidence we may already have seen. Conformal cyclic cosmology suggests that violent events in the previous universe, such as the collisions of supermassive black holes, could leave imprints in our cosmic microwave background. These imprints would appear as faint, circular patterns, concentric rings scattered across the sky, where the temperature variations differ just slightly from the surrounding regions. These rings, if real, would be cosmic fossils. Not fossils of galaxies or stars, but fossils of events that occurred before the Big Bang. Several researchers have claimed to find exactly such circles. Perfectly round, low-variance rings. Some appear clustered. Some appear isolated. Some look like ripples frozen into the cosmic fabric, like the remnants of gravitational waves from a previous aeon echoing across the boundary into ours. The scientific community debated fiercely. Were these patterns real? Statistical artifacts? Coincidences? Noise? The controversy only made the possibility more mesmerizing. Because if even one of these rings is genuine, it rewrites the history of existence. Imagine for a moment what that means. Right now, as you look into the cosmic microwave background, the oldest light we can see, you might be seeing, embedded within it, the shadows of black holes that lived and died before our universe was born. Structures not from 13.8 billion years ago but from an age beyond measurement. Events that happened in a cosmos that no longer exists. This realization carries a chill. It means we live inside a universe that is not isolated. Our universe is part of a lineage, a chain. A cosmic ancestry stretching back through countless eons, each universe passing information into the next, each adding its own chapter to an infinite story. Envision that chain. Aeon after aeon. Universes rising, expanding, cooling, dissolving. Black holes forming, merging, vanishing. Radiation spreading into infinity. Then, quietly, seamlessly, the transition. A new universe ignites from the ashes of the old one. Time, in this vision, is both endless and cyclical. Each aeon is unique yet connected. Each universe inherits the ghostly imprints of the last, but also begins with its own possibilities. This changes everything about how we see our place in the cosmos. We are not the first intelligent beings to ponder existence. We may not be the first to ask about beginnings. Our entire universe may be the descendant of countless prior worlds, each one experiencing life, death, and transformation. As you explore this idea, the line between science and philosophy softens. What is a beginning if beginnings are merely continuations? What is an ending if endings are simply gateways? What does it mean for time to stretch infinitely forward, yet still repeat in cycles too vast for the human mind to grasp? And what secrets lie in the traces the previous aeon left behind? Some physicists speculate that not only black hole collisions but also the decay of dark matter or massive cosmic events near the end of the previous aeon could ripple into ours. These ripples might shape the initial conditions of our universe, influencing how galaxies form, how structures emerge, maybe even how life becomes possible. The thought is staggering. The arrangement of stars in our sky may have been influenced by processes that happened before our universe existed. In this vision, we are the inheritors of a cosmic legacy that stretches beyond time. Our universe carries the memories of an older cosmos, not direct memories but subtle hints, faint echoes encoded in radiation and structure. And one day, far in the future, our universe will leave its own echoes behind, seeds for the next aeon to follow. There is beauty in this continuity, a sense of cosmic immortality, a feeling that even though universes die, the story never ends. Something always persists. Light, patterns, information, passing across the boundary like whispers through eternity. Yet there is also a sense of haunting humility. Our universe may be vast, ancient, and awe-inspiring, but it is still just one chapter in an infinite book. And as you gaze into the faint glow of the cosmic microwave background, the thought becomes almost unbearable. What if the universe we see is only a shadow? What if our cosmos carries the fingerprints of worlds long gone? And what if, in the echoes written across the sky, the past is calling out to us, waiting to be understood? Imagine diving into a realm where the familiar rules dissolve, where time loses meaning, and where space no longer behaves like the soft, continuous fabric we think it is. This realm is the quantum world, a place where certainty vanishes and possibility takes over. To understand what the universe might have been before the Big Bang, we must step into this strange domain, because at the deepest level, the beginning of everything was governed not by classical physics, but by quantum reality. Picture yourself approaching the earliest moment of the universe. With every step you take backward in time, order begins to unravel. Clocks tick faster, then slower, then not at all. Space shrinks, then ripples, then fractures into something unrecognizable. Eventually, you reach a point where gravity is no longer the gentle curve of spacetime described by Einstein. Instead, it becomes jittery and restless, fluctuating unpredictably, as if the universe itself is trembling. This is the realm where time breaks. In classical cosmology, the neat, orderly world of general relativity, time is a smooth dimension stretching from past to future. Every moment follows another in a sequence. But in quantum cosmology, time is not fundamental. It is emergent. It arises only when the universe is large and structured enough to support its flow. Before that structure exists, time becomes slippery. Imagine a movie played so slowly that each frame is disconnected from the next. Now imagine the frames appearing out of sequence or repeating or vanishing entirely. This is closer to how the early universe behaved. Not as a continuous flow, but as a cloud of potential states, each one possible, none yet realized. In this chaotic quantum landscape, the usual question, what happened before the Big Bang? Becomes meaningless. Not because nothing existed before, but because before itself requires time, and time may not have existed in any familiar sense. Instead of a sequence of events, the pre-Big Bang universe might have been a timeless quantum state, a kind of cosmic seed filled with potential energy, possibility, and uncertainty. This state is often described as a quantum vacuum, but the word vacuum is misleading. It does not mean emptiness. It means a seething ocean of fluctuations, where particles flicker into existence and vanish, where fields rise and fall, where spacetime itself vibrates. This quantum vacuum could have existed eternally, not in time as we know it, but in a state of timeless equilibrium. A universe not yet unfolded. A cosmos holding its breath. Then something happened. Not an explosion, not a detonation, but a quantum transition. Visualize this moment. A fluctuation becomes large enough, powerful enough, coherent enough to ignite a change in the structure of reality. A bubble of classical spacetime forms within the quantum sea. Inside that bubble, time begins. Space begins. Causality begins. This bubble becomes our universe. To anyone inside it, the moment feels like a beginning. But from the perspective of the timeless quantum state, it is simply a transformation. This quantum transition is what many scientists believe we misinterpret as the Big Bang. The creation of spacetime from quantum fluctuations produces enormous energy, heat, radiation, and expansion, effects that mimic a cosmic explosion. But nothing exploded. The universe didn't burst from nothing. It crystallized from the quantum fog. This idea carries profound implications. It means the universe might not need a creator or an initial cause. It means the laws of physics themselves may have emerged with time. It means the question of why the universe exists transforms into why the quantum state allowed our universe to form. And it means that the Big Bang is not the origin of everything, only the origin of classical time. The earliest state of the universe may have been like a strange, shimmering dream, neither material nor immaterial, neither evolving nor static, neither dead nor alive. A haze of probabilities waiting to become reality. As you try to imagine this, the human mind strains. Time is so deeply rooted in our psychology that the idea of a timeless origin feels almost impossible to grasp. But consider this, the deepest layers of physics do not care about human intuition. They follow laws that transcend our concepts. In quantum mechanics, particles can exist in multiple states at once, leap across space without crossing the space in between, and influence each other instantaneously across cosmic distances. If matter behaves this strangely, why shouldn't time? The quantum view suggests that time is a latecomer, a product of the universe becoming large, stable, and classical. Before that, the universe existed in a state beyond time, beyond sequence, beyond story. In this view, the birth of the universe is not the start of a timeline but the start of the timeline. The difference is subtle but immense. As you drift deeper into this idea, a quiet, unsettling possibility emerges. Our universe may be just one of countless quantum transitions happening in the timeless vacuum. Each bubble a new cosmos. Each cosmos with its own flow of time. Each timeline starting from a moment that feels like a beginning but is actually just a local transformation in an eternal, timeless background. And so the quantum perspective leaves you with a final, haunting thought. The universe did not begin in time. Time began in the universe. Imagine floating at the edge of everything you have ever known, staring beyond the boundary of our universe. Not into empty darkness but into a vast, unending sea. A place where entire universes rise and fall like waves. Each one expanding, evolving, collapsing, or drifting forever. Each one governed by its own laws, its own forces, its own beginning and its own fate. This is the multiverse, not a fantasy, not a sci-fi concept, but a serious scientific possibility that emerges naturally from some of the deepest theories in modern physics. To understand the multiverse, you must first let go of a deeply held assumption, that our universe is all there is. For most of human history, this idea felt natural. The stars, the galaxies, the cosmic background, they seemed to form a closed system, a single cosmic bubble containing everything. But as science pushed further into the fabric of reality, cracks appeared in that comforting idea. Cracks that hinted at hidden realms beyond our cosmic horizon. Imagine looking at our universe from a higher dimension, like looking down at a soap bubble floating in a sea of countless other bubbles. Each bubble is a universe. Each universe has its own beginning. Some inflate rapidly. Others collapse quickly. Some are rich with stars and galaxies. Others remain dark, cold, and empty. Ours is simply one bubble that formed under a specific set of conditions. Conditions that allowed matter, structure, and life to emerge. The multiverse idea does not come from speculation alone. It arises from different branches of physics, each pointing toward the same breathtaking possibility. One path begins with cosmic inflation. As scientists studied inflation more deeply, they discovered that it may not stop everywhere at once. Instead, in many models, inflation continues eternally in vast regions of space, even while it ends in smaller pockets. Those pockets become universes, bubbles within an ever-growing cosmic foam. Our universe is one such bubble, surrounded by countless others. Inflation becomes a universe-generating engine, sculpting a multiverse with endless variety. Another path comes from string theory, which proposes that the fundamental particles of our universe are not points but tiny vibrating strings. These strings require extra dimensions, hidden dimensions curled up beyond our perception. And within this higher dimensional landscape, there isn't just one possible universe. There are trillions upon trillions of possible configurations, each one corresponding to a different universe with its own unique properties. String theory's landscape is so vast that it practically demands a multiverse to contain it. Yet another path emerges from the quantum world. Quantum mechanics tells us that particles do not follow a single path from past to future. They explore every possible path at once. Some interpretations propose that these possibilities are not merely mathematical, they are real. Every quantum event branches into multiple outcomes, each outcome becoming a new universe. In one universe, a particle moves left. In another, it moves right. In one universe, a star explodes. In another, it does not. In one universe, life evolves on Earth. In countless others, it never appears. These different pathways converge on the same unsettling idea. Reality is far larger, far stranger, and far more layered than a single universe. Imagine drifting through this cosmic sea. You pass through regions where the laws of physics twist into unfamiliar shapes. Universes where gravity is stronger, pulling stars into violent collisions. Universes where gravity is weaker, preventing galaxies from forming at all. Universes glowing with radiation. Universes shrouded in eternal darkness. Universes expanding forever. Universes collapsing inward. In some of these universes, time flows differently. In others, chemistry never evolves beyond simple atoms. Some universes are so alien that even imagination fails to grasp them. Our universe feels special, because we live in it, because it contains us, because its laws allow for complexity and consciousness. But within the multiverse, specialness becomes relative. Most universes may be empty or sterile. Only a tiny fraction may have the delicate balance required for stars, planets, and life. And yet, those rare universes exist, because the multiverse provides endless chances for existence to take shape. This idea generates a powerful emotional contrast. On one hand, wonder, the notion that reality is an infinite ocean of possibilities, far richer than anything we could imagine. On the other hand, existential smallness, the knowledge that our universe may be just one drop in that vast sea. A beautiful drop, a meaningful drop, but a drop nonetheless. And yet, there is a quiet comfort within that vastness. Because in the multiverse, nothing is alone. Nothing is isolated. Existence becomes a great cosmic tapestry, each universe a thread woven into the totality of reality. Now imagine the boundaries between universes. Not hard walls, but transitions, collisions, connections. Some theories suggest that universes might occasionally bump into one another. A collision could leave circular imprints in the cosmic microwave background, faint scars across the sky indicating that our universe once brushed against another. Some scientists have even searched for such patterns. A few have claimed to find hints, just enough to spark debate, tension, and fascination. Other theories propose that black holes might serve as portals to new universes. When a star collapses into a black hole, it forms a singularity, or so we thought. Some models suggest that the singularity is not a dead end. Instead, it becomes a quantum bounce, creating a new universe on the other side. In that case, every black hole in our universe could be the seed of another universe entirely, each one branching off into its own cosmic timeline. Our universe, too, could be the child of a black hole that formed in another universe long before ours existed. Imagine that lineage. A family tree of universes, each generation producing countless descendants. Each universe shaping the next through deep, hidden physics. Each one connected through a chain of creation that stretches beyond imagination. The multiverse challenges the very essence of identity and existence. If there are infinite versions of the universe, are there infinite versions of you? In some branches of the quantum multiverse, yes. There are universes where every possible choice you could make has been made. Universes where different histories unfolded. Universes where different futures await. But in other versions of the multiverse, such as the inflationary or string landscape multiverses, there are no duplicates of you at all. The conditions are too different. The laws too alien. Your existence is unique to this universe, to this particular arrangement of forces and atoms. This complexity invites both awe and humility. You are unique, and yet you are part of something infinitely vast. As you drift through the cosmic foam of universes, a deeper question emerges. If the multiverse is real, what does that make the Big Bang? In the multiverse, the Big Bang is not the beginning of everything. It is the beginning of our bubble, our slice of reality, our local chapter in a boundless book. The multiverse reframes the Big Bang as one event among countless others, each universe birthing its own cosmic expansion in an unending symphony. And then, a final haunting question rises slowly from the depths of this idea. If our universe is just one bubble in the cosmic sea, what lies beyond even the multiverse itself? What kind of reality contains a reality this vast? And is there a limit to how deep existence goes? Or is the true nature of reality forever beyond our comprehension? The multiverse invites us into a story larger than any beginning, larger than any end, larger than any universe we could ever imagine. Imagine holding a clock in your hand and watching its second hand sweep forward, smooth and relentless. It feels so natural, so inevitable that you never question it. Time moves. Time flows. Time carries everything toward the future. But what if this feeling is an illusion, an artifact of consciousness rather than a feature of the universe? What if time, as we experience it, is not fundamental at all? To understand this, you must step outside the human experience and see time not as a river but as a landscape. Imagine a vast cosmic mountain range. Every moment, past, present, and future, is a peak or valley already existing in that landscape. You are not moving across it. You are simply seeing different parts of it depending on where you stand. The flow of time is not something the universe does, it is something your mind creates as it processes one slice of that landscape after another. This idea, known as the problem of time, haunts the deepest layers of modern physics, because when scientists attempt to merge quantum mechanics with general relativity, time begins to behave strangely, too strangely. Equations that govern gravity work perfectly without any reference to time at all. They describe a universe that simply is, not one that becomes. Meanwhile, quantum mechanics insists on probabilities evolving in time. When these theories try to coexist, time seems to vanish from the equation entirely. It slips away, leaving behind a reality without a ticking clock. Imagine a universe without time. Galaxies still exist, stars still burn, but not in a sequence. Not in a story. Instead, it's all there simultaneously, every event, every configuration, every possibility, arranged like pages of a book you can flip through but that does not write itself as you read it. Our sense of past and future becomes a trick of limited perception, like watching frames of a movie one by one and assuming the story is unfolding because you cannot see all the frames at once. This view of a timeless universe forces a dramatic shift in how we imagine the origin of everything. If time is not fundamental, then the concept of a beginning loses meaning. The Big Bang stops being the first moment and becomes a point on the landscape, a location, not an initiation. The question, what came before the Big Bang, becomes as meaningless as asking, what is north of the North Pole? Not because nothing exists there, but because the question itself is built on assumptions that don't apply. Picture a cosmic tapestry stretched across eternity, with each event embroidered into the fabric. Our minds follow a thread through the tapestry and call that the passage of time. But the tapestry exists all at once. The thread is simply our trajectory through a timeless structure. To understand how unsettling this is, imagine watching a glass fall off a table in slow motion. You see the glass wobble, tilt, slip, and descend. You see it shatter into fragments on the floor. Every stage appears to cause the next, creating a chain of effects. But in a timeless universe, all these configurations, the glass standing, tilting, falling, shattering, exist together in the cosmic landscape. Your mind stitches them into a narrative of cause and effect, but the universe itself does not require that narrative to exist. And this raises a haunting possibility: the universe may not be evolving. We may be the ones doing the evolving. The physics of timelessness suggests that now is not special. Every moment feels like now to the observers living inside that moment. From the perspective of the cosmos, they all exist with equal reality: your birth, your death, the death of stars, the birth of new ones, the rise and fall of civilizations. Time becomes a dimension of existence, not a flowing current. Yet this vision of timelessness carries a powerful emotional contrast. On one hand, it evokes awe, because it suggests the universe is far more structured and profound than we ever imagined. On the other hand, it evokes fear, because it strips away the comforting illusion of progress, narrative, and direction. Without time, what becomes of meaning? What becomes of purpose? What becomes of the idea that the universe began, evolves, and will one day end? But the disappearance of time does not erase mystery. It deepens it. If time is emergent, something that arises only when the universe reaches a certain scale, then the earliest moments of the cosmos were not moments at all. The universe may have existed in a state of pure potential, unbound by sequence. Only when it expanded, cooled, and formed structure did time crystallize into the familiar form we know. Imagine watching time freeze, not because something went wrong but because the universe became too small, too hot, too chaotic for time to exist. Then imagine watching time emerge, like mist rising from a cooling lake, as the cosmos grows large enough for the laws of physics to lock into place. In this view, the Big Bang is the moment when time becomes meaningful, not the moment when existence begins. This changes everything. If time is not fundamental, then the birth of the universe was not a first moment. It was a transition, a phase change, like water freezing into ice. A shift in the underlying structure of reality. Before that, the universe existed, but not in any sense we can describe with clocks, sequences, or causality. Asking what happened before becomes like asking what shape ice was before it froze. The answer is, the question itself misunderstands the process. This view forces us to reconsider our deepest assumptions. We see ourselves as travelers on a timeline. But in a timeless universe, we are not travelers. We are locations in a vast, eternal structure. And as you contemplate this, a strange realization dawns. The universe may not have a beginning. It may not have an end. It may simply be timeless, infinite, and forever beyond the reach of the clocks we carry in our minds. Time, the most familiar dimension we know, may be nothing more than the lightest shadow cast by a reality we are only beginning to glimpse. Imagine traveling back to a moment when the universe was so young, so hot, and so chaotic that the familiar building blocks of reality, particles, atoms, forces, did not yet exist. A moment when everything was compressed into a glowing sea of raw energy. No galaxies. No stars. No planets. Just a furious, swirling storm of potential waiting to crystallize into the universe we know. This moment is not the Big Bang itself but what followed, a fraction of a second later, when the birth of forces and matter reshaped the cosmos forever. But as we peer into this era with the eyes of modern physics, we discover something unsettling. The emergence of matter and forces may not have unfolded the way we once imagined. Instead of a smooth, simple creation, the universe may have undergone a series of dramatic transitions, cosmic events that hint at a far deeper and more mysterious origin. Picture the earliest phase of the universe as a state of pure symmetry. In this state, all forces, gravity, electromagnetism, the nuclear forces, were unified. There were no distinctions, no differences, no separations. Everything was governed by a single, elegant rule. It was a moment of perfect balance, a symmetry so complete that nothing we recognize today could have existed within it. But perfect symmetry is inherently unstable. Imagine holding a pencil balanced perfectly on its tip. The slightest disturbance causes it to fall, breaking the symmetry and choosing a direction. The early universe behaved the same way. As it expanded and cooled, this perfect symmetry shattered. And from that shattering, the universe's fundamental forces separated, gravity first, then the strong nuclear force, then the electroweak force, and finally the familiar split between electricity and magnetism. Each break was a cosmic event. A phase transition of unimaginable scale. A transformation not unlike water freezing into ice, but happening across the entire cosmos. Visualize this process as a grand unfolding. The universe cooling just enough for a new force to emerge, then cooling further for particles to stabilize, then further still for the first atoms to form. The cosmos did not simply come into being. It descended through layers of symmetry breaking, each one revealing new structure and new possibilities. In this cascading sequence, particles were born, not all at once but in a violent, chaotic ballet. Quarks flickered into existence, then bound together to form protons and neutrons. Electrons danced into being and locked into orbit around these nuclei. Light, once trapped in the dense plasma, finally broke free when atoms formed, illuminating the universe. These events are often described in textbooks with calm diagrams and neat equations. But in reality they were anything but calm. They were turbulent, explosive, and unpredictable. The universe was a cauldron of collisions, annihilations, creations, and transformations. An ocean of fire, shaped by forces that were themselves still evolving. And yet, even as this magnificent sequence unfolds in our imagination, new questions arise, questions that challenge the foundation of the story. Why did the universe break symmetry the way it did? Why did matter emerge in the quantities it did? Why do the forces have the exact strengths they have today? If any single parameter were even slightly different, if the strong nuclear force were weaker, if electromagnetism were stronger, stars would never form, atoms would not exist, and life would be impossible. Feels too precise, too delicate, too finely tuned. Physicists call this the fine-tuning problem. And it suggests that the emergence of forces and matter might not have been an accidental outcome of cooling, but the result of deeper rules, rules that existed before the Big Bang or beyond it. Imagine if the universe inherited its structure from a previous cosmic era. If the strength of forces and the masses of particles were not randomly set at the Big Bang, but passed down from a previous universe, carried like genetic traits through cosmic transitions. If the universe's apparent fine-tuning is not luck, but lineage. Or imagine that the laws of physics themselves emerged from a deeper, hidden principle. A principle that governs not just our universe but all possible universes. In this view, the forces we know today are like the visible branches of a much larger tree whose roots lie far beyond the reach of our observations. This possibility transforms the narrative. The birth of forces and matter stops being a simple consequence of cooling and begins to look like the outcome of a deeper cosmic architecture. An architecture we barely understand. Even the matter around us carries a haunting mystery. Why is there more matter than antimatter? In the early universe, particles and antiparticles should have been created in equal amounts. They should have annihilated each other completely, leaving behind nothing but light. And yet, a tiny imbalance, roughly one extra matter particle for every billion particle-antiparticle pairs, gave rise to all the matter in the universe. Why did this imbalance occur? What mechanism tilted the scales in favor of matter? And where, if anywhere, did that mechanism originate? Some theories suggest it was the result of spontaneous symmetry breaking, an accidental tilt in the early universe. Others propose deeper causes, quantum processes beyond our current models, or remnants of events that took place before the Big Bang. Whatever the answer is, it forces us to confront the possibility that the emergence of matter was not a natural inevitability but a cosmic choice, perhaps influenced by physics we have not yet discovered. As the universe continued to expand and cool, the complex structures of forces and particles locked into place. Gravity became the architect of galaxies. Electromagnetism sculpted atoms and molecules. The nuclear forces powered stars. These forces created the framework for everything we see today. But beneath this familiar structure lies a quiet, unsettling realization. The universe we know is only one version of what could have emerged. If symmetry had broken differently, if forces had split in another order or with different strengths, our universe would be unrecognizable. Maybe lifeless. Maybe structureless. Maybe without time, matter, or even space. The birth of forces and matter is not just a chapter in the universe's history, it is the defining moment that shaped its destiny. And the more we study it, the more we sense that this moment was influenced by something deeper, something hidden in the physics of the earliest cosmic phases or in the echoes of universes long gone. As you stand at the edge of this mystery, one question emerges, vast and irresistible. What shaped the laws that shaped us? And could those laws be the fingerprints of a universe that came before? Imagine peeling back the visible universe like the surface of a painting, layer by layer, until you reach the hidden scaffolding beneath it. What you find there is not matter, not energy, not space or time, but something far more abstract. Patterns, relationships, information. A silent architecture that does not glow, does not move, yet underlies everything that exists. This invisible structure is the hidden architecture of space-time, and it may be the deepest mystery in modern cosmology. For most of human history, we imagine space as an empty stage where the universe performs its drama. Time was the steady rhythm that guided the story forward. But physics has begun to whisper a different truth. Space might not be fundamental. Time might not be fundamental. Instead, both may emerge from something more primitive, something woven from pure information. Imagine space-time not as a smooth fabric, but as a tapestry of microscopic threads, loops, nodes, or quantum grains that form the underlying geometry of reality. These elements are so small they are beyond the reach of any microscope, beyond the reach of light itself. Yet every point in space is built from them, every second of time is generated by their interactions. Picture walking through a forest and not realizing that what looks like a continuous landscape is actually made of countless leaves, twigs, and grains of soil. In the same way, spacetime appears continuous, smooth, and unbroken, but only because its fundamental pieces are too tiny for us to see. This idea reveals itself in many forms. In loop quantum gravity, spacetime is made of discrete loops of geometry, tiny quantized chunks of area and volume. In the holographic principle, spacetime emerges from information stored on a boundary surface, like a cosmic hard drive encoding everything inside. In quantum entanglement models, the connections between quantum states themselves give birth to space, binding the universe together like threads of an invisible web. Each theory offers a different metaphor, but they paint the same breathtaking picture. Spacetime is not fundamental. Imagine staring at the night sky. You see stars scattered across a dark canvas. But what if that canvas is not truly empty? What if it is built from a deep, vibrant network of quantum interactions? What if the fabric of reality is more like a code, a kind of cosmic software running on a substrate we have yet to fully grasp? This idea becomes even more haunting when you consider black holes. In the classical view, black holes swallow everything: matter, light, even information. But according to quantum theory, information cannot be destroyed. So where does it go? Some physicists believe the information becomes encoded on the event horizon, the surface of the black hole. If true, then a black hole is not a void but a data vault. Every particle, every event that falls inside leaves an imprint. And if information forms the basis of spacetime, then black holes are not just cosmic monsters. They are windows into the universe's fundamental operating system. Imagine space itself being woven from these informational imprints, each bit of data contributing to the emergence of geometry and gravity. In this vision, gravity isn't a force but an illusion, an emergent property, like the surface tension of water arising from interactions among countless tiny molecules. You begin to see the universe not as a physical machine, but as a computational one. A system where spacetime, matter, and energy are manifestations of deeper informational rules. And if the universe is fundamentally informational, then its origin may not be a matter of particles or explosions, but of patterns crystallizing into structure. This raises a profound possibility. Perhaps the Big Bang did not create spacetime. Perhaps spacetime unfolded from information already present, an emergent phenomenon rising from deeper layers of reality. Before the geometry of our universe existed, there may have been pure entanglement, pure correlations, pure potential. The architecture of spacetime may have grown out of that raw informational sea, the way a crystal grows from a solution. Imagine watching this emergence from a vantage point beyond time. At first, nothing resembles the universe. No space. No distance. No location. Instead, a network of quantum states flickers chaotically, interacting in patterns too complex to comprehend. Slowly, as the network grows, certain structures stabilize. Connections strengthen. Regions differentiate. A geometry begins to form, not from material but from relationships. Space is born from connections. Time is born from change. Reality is born from information. This idea is both exhilarating and terrifying. It means that the universe we see is merely the surface of a deeper reality that does not resemble space, time, or matter in any familiar sense. We are like characters in a story who only glimpse the words on the page, not the author, not the ink, not the structure of the book. But this hidden architecture is not just theoretical. Experiments hint at its existence. In certain materials, scientists have observed phenomena where space-like behavior emerges from quantum entanglement patterns. Simulations demonstrate how geometry can arise from information networks. And black hole thermodynamics shows that the amount of information on a surface determines the volume it encloses, a clue that the universe may indeed be holographic. If this is true, every location in space exists because of the way information is arranged. Every moment in time flows because of how these relationships evolve. Every particle, every atom, every galaxy is a ripple on a deeper informational sea. And that leads to a breathtaking question. If spacetime is emergent, then what is it emerging from? A timeless quantum state? A previous universe? A deeper multiversal structure? A fundamental code woven into the fabric of reality? The hidden architecture of spacetime becomes not just a scientific puzzle, but a cosmic doorway. A path toward understanding what lies beneath the universe we know. And as you stand at the threshold of that doorway, one thought lingers with quiet intensity. The universe we see is not the universe that is. It is only the surface of something far deeper, a hidden architecture waiting to be revealed. Imagine drifting through the vast darkness between galaxies, where space feels endless and silent, only to sense, just faintly, that something else is there. Not another star. Not another galaxy. Something larger. Something older. Something brushing against our universe from the outside, like the shadow of a distant world passing behind a thin veil. This is the unsettling idea behind models in which our universe was never alone. To most of us, the universe feels self-contained. A sealed reality. A bubble of spacetime expanding into nothingness. But modern cosmology suggests that this bubble may be one among many, each universe a membrane or brain, floating in a higher dimensional space. In this vast dimensional ocean, universes can drift, ripple, collide, or interact. And such interactions could have shaped the fate of our cosmos long before the first stars ignited. Imagine our universe as a vast sheet, thin, flexible, and stretching across dimensions we cannot see. Now imagine another sheet running parallel to ours, so close that the distance between them is smaller than the width of an atom. These two sheets are invisible to each other except through gravity, the only force strong enough to leak between dimensions. Most of the time they drift peacefully. But sometimes the sheets ripple. Sometimes they wobble. And sometimes they collide. Now imagine a collision of universes. Not a violent explosion like the Big Bang, but an unimaginable press. Two vast cosmic membranes slamming into each other with such force that the impact releases extraordinary energy. That energy floods through the brains, igniting radiation, matter, and expansion. According to some models, this collision was the Big Bang. Our universe's birth may have been the shockwave from two higher-dimensional worlds brushing together. In this picture, the Big Bang wasn't the beginning of everything, it was the aftermath of a cosmic encounter. This idea, called brain cosmology, is both breathtaking and terrifying. It suggests that the deepest origins of our universe lie not in a singularity, nor a quantum foam, nor a bounce, but in the geometry of dimensions beyond our senses. Imagine the moment two universes collide. Space-time ripples like water struck by a stone. Energy surges across the membranes. For a fraction of a second, the entire structure of the universe vibrates with impossible intensity. Patterns of density are carved into the newborn cosmos. Patterns that eventually grow into galaxies, clusters, and cosmic structure. Those ripples may still be visible today as faint anomalies in the cosmic microwave background, whispers of a collision older than time as we know it. Some physicists believe such imprints already exist. Certain cold spots, strange alignments, or large-scale asymmetries in the cosmic afterglow might be the scars of another universe brushing against ours. If that is true, then our universe still carries the fingerprints of its cosmic neighbor, ghostly traces hidden in ancient radiation. But this idea goes further. If other universes exist, then they may still be close. They may drift near ours in the higher dimensional space. Their gravity may tug at the edges of our cosmos, pulling just enough to create unexplained motions or distortions. Some astronomers have even suggested that the mysterious dark flow, a strange bulk movement of galaxy clusters, could be caused by the gravitational pull of a massive structure outside our observable universe. Something so large and so dense that it warps our cosmos from beyond the horizon. Picture a colossal, unseen world passing near ours like a silent giant. We cannot see it, but its presence bends the path of galaxies and reshapes the motion of clusters. A cosmic shadow cast from a universe next door. This possibility blurs the boundaries between universes. It suggests that our cosmos is not isolated, but part of a dynamic environment, a crowded dimension where universes interact like drifting continents. Other theories imagine even more dramatic interactions. Perhaps universes collide not once, but periodically, creating cycles of cosmic creation. Or perhaps universes can merge, blending their physical laws into new combinations. Some models even propose that universes can bleed energy into each other, creating subtle imbalances or variations in the cosmic background. Imagine energy seeping across dimensions like vapor crossing a thin membrane. Imagine particles slipping between universes, rare but possible. Imagine gravity leaking outward or inward, tugging at the fabric of spacetime like a tide. Suddenly, the idea of a self-contained universe feels small, almost provincial. The emotional effect of this shift is profound. It means our universe is not the whole of existence. It is part of a larger structure, maybe infinite in scale, maybe intricate in pattern, maybe alive with interactions we barely understand. And then comes the ultimate question. If universes can touch, can life or information pass between them? Some thinkers speculate that quantum entanglement might exist between universes. That certain deep connections, formed when universes were once connected or overlapping, might survive even after separation. In this vision, entangled particles could reach across universes, sharing states in ways we cannot perceive. Others imagine that consciousness itself might be influenced by higher dimensional structures. That the fabric of thought, the feeling of existence, the spark of awareness might be tied not only to our universe's physics but to something deeper connecting multiple universes. This is speculative, but the idea lingers like a quiet whisper. If universes interact, perhaps reality is more entangled than we dare imagine. In this framework, our universe becomes a participant in a cosmic environment, not an isolated creation. We are part of an ecosystem of universes. Some older, some younger, some vastly different in laws and structure. Our universe has neighbors, and those neighbors may have influenced our earliest moments. And it raises a haunting possibility. Perhaps another universe touched ours, leaving clues we have yet to fully understand. Perhaps another universe shaped our fate long before stars formed. Perhaps our universe carries the memory of that encounter. Some cosmologists propose that the Big Bang itself was the moment of contact between universes, a collision so vast that it ignited everything we see today. Others suggest that small touches, gentle, subtle influences, have occurred since then, bending our cosmic fabric in ways we have not yet recognized. And yet, amid all these possibilities, one thought rises above the rest. If the universe we live in was not alone at its birth, then we are children of a cosmic interaction, creatures shaped not by one universe but by two. The idea is both humbling and strangely beautiful. It means that our existence may be the result of a cosmic meeting, an intersection of worlds that set the stage for everything that followed. As you contemplate this, a quiet question emerges, trembling with possibility. If our universe has touched another before, could it happen again? And if it does, what new cosmic story will unfold in the shadows where two universes meet? Imagine standing at the edge of cosmic history, staring back across 13.8 billion years, expecting to see a beginning, a single spark that ignited everything. But instead of a clear starting point, the past dissolves into something stranger. Not a moment of creation, but a transition. A shift. A change in state. A transformation without a true origin. The more deeply scientists stare into the earliest moments of the universe, the more a radical idea begins to take shape. Maybe the universe never truly began at all. Picture the universe not as a story with a first page, but as a vast mural with no clear corner. A painting that extends beyond the frame we can see. For most people, the Big Bang feels like a definitive moment, the ultimate beginning. But when we follow the equations of physics all the way back, they don't stop cleanly at the bang. They don't point to a creation point. Instead, they curve, twist, and approach a boundary that looks less like a beginning and more like an edge of our understanding. Now imagine a world without beginnings. A universe where events do not spring from nothingness but from previous states, previous structures, previous phases. A universe where before is not forbidden, just inaccessible. A universe where the Big Bang is simply a door we cannot open, a veil that hides not emptiness but more reality beyond. This idea, that the beginning is an illusion, is not born from fantasy. It emerges naturally from the mathematics of quantum cosmology, from the geometry of spacetime, from the behavior of entropy, and from the profound possibility that time itself may be emergent, not fundamental. The deeper we go, the more the illusion cracks. Picture the earliest universe as a state of incredible density and heat. But what if this state wasn't a singularity, not a point of infinite compression, but the echo of a previous universe collapsing, smoothing, transforming, and finally crossing into a new phase? In such models, the Big Bang is not a beginning but a bounce, a transition between eras of cosmic existence. The arrow of time resets, but the universe itself continues. Or imagine that time did not flow in the earliest moments. That the universe existed as a quantum haze, timeless and unstructured, until some threshold was crossed and time switched on. If time didn't exist before that moment, then the idea of a beginning becomes meaningless. You cannot have a first moment in a reality where moments themselves had not yet formed. This realization carries both wonder and discomfort. On one hand, there is awe, the possibility that existence is eternal, that the cosmos is not a miracle born from nothing but a phenomenon without beginning or end. On the other hand, there is a quiet dread, because the human mind craves origins. We want a first cause, a clean point where everything starts. The illusion of a beginning comforts us. It gives the universe a story we can grasp. But what if reality refuses to fit that story? Imagine a cosmic ocean stretching infinitely in both directions. We, living inside one wave of expansion, mistake the crest for the beginning. The trough before it is hidden from us, swallowed by the laws of physics that break down under extreme conditions. But just because we cannot see beyond the crest does not mean there was nothing there. Now imagine time as a circle rather than a line. A loop where the end feeds into the beginning. A universe that cycles endlessly, each era giving birth to the next. In such a world, the question, when did it begin, is as meaningless as asking which point on a circle is first. Or imagine a multiverse where countless universes form continuously, eternally, without a first moment, each sprouting from quantum fields or higher dimensional collisions. Our universe would be just one blossom in an infinite cosmic garden. In every version of this deeper reality, the Big Bang loses its throne as the absolute beginning. It becomes a doorway, not a creation. As this realization settles in, a quiet, transformative thought begins to form. The universe may not need a beginning. It may not have ever been nothing. It may simply be eternal, cyclical, emergent, or woven into something deeper than time itself. And in that possibility lies a profound truth. The beginning we cling to may be nothing more than a story told by our limited perspective, a story the universe itself never wrote. Imagine standing inside a vast observatory, the dome open to the cold darkness of space, as new data streams in from telescopes scattered across the Earth and orbiting silently above it. Each beam of light captured, each gravitational wave recorded, each faint background photon measured carries a message from the edges of time. And lately those messages have grown strange, subtle, unsettling. They whisper of patterns that don't belong, anomalies that resist explanation, clues that suggest the Big Bang might not be the universe's final word after all. For years, the scientific community believed the Big Bang model was complete. Not perfect but powerful. It explained the cosmic microwave background, the expansion of space, the formation of galaxies, the abundance of elements. But as new instruments sharpened humanity's vision, the universe began revealing details that did not fit neatly into this familiar narrative. Imagine looking at the cosmic microwave background, the faint, ancient glow left over from the young universe, and noticing something odd. A cold region, far larger and colder than expected, as if some enormous structure or event disrupted the early cosmos. This cold spot, first dismissed as statistical noise, has persisted across increasingly precise measurements. Its size, shape, and temperature profile defy the simplicity of the standard model. Some scientists have speculated it could be the imprint of another universe brushing against ours, or the scar of a cosmic phase change before the Big Bang. Then there are the strange alignments, eerie correlations across vast distances in the cosmic background radiation. Patterns that seem too coherent to arise by chance. Certain hot and cold regions form axes, pointing in directions that should be random but are not. These mysterious alignments, sometimes called the axis of evil, challenge the assumption that the early universe was perfectly uniform. Something may have shaped the cosmos before its expansion even began. But the anomalies do not stop at ancient light. Gravitational wave observatories like LIGO and Virgo detect ripples from merging black holes, collisions so violent they distort spacetime itself. Among these detections are massive black holes that should not exist so early in the universe's timeline. Their origins are too abrupt, their masses too large. It's as if the universe inherited structures or seeds from a time before the Big Bang. Perhaps they formed in a previous cosmic era and survived the transition into ours. Meanwhile, the James Webb Space Telescope peers deeper into the early universe than any instrument before it. And what it finds is astonishing: galaxies forming far too early, far too bright, far too massive to fit the standard timeline. Their existence suggests the early universe was more structured, or older in some sense, than expected. The cosmic story appears to begin too mature, too quickly. Like opening a book and finding the first chapter halfway through. Each new piece of evidence bends the narrative, pulling the Big Bang away from its pedestal as the ultimate origin and repositioning it as one moment in a broader tapestry. Another mystery emerges from the distribution of dark matter, the invisible substance shaping galaxies and cosmic structure. In several surveys, astronomers have discovered enormous, unexpectedly coherent structures spanning billions of light-years. These formations, called cosmic walls, or great attractors, appear almost too large to form within the time allowed since the Big Bang. Their sheer scale hints at pre-existing organization or influence, perhaps a residue of physics from before the Big Bang, baked into the initial conditions of our universe. Then there is the issue of entropy. According to the second law of thermodynamics, entropy, disorder, always increases. Yet the universe began in a state of incredibly low entropy, an extraordinarily ordered condition. What mechanism created such order? And how could such a finely tuned state arise spontaneously from nothing? Unless, of course, it didn't arise spontaneously. Unless it was inherited. Many theories propose that the low entropy of our universe is the final chapter of a previous cosmic cycle, a transition from collapse to expansion. Others suggest it was sculpted by deeper laws or previous eons. Even quantum cosmology implies that the earliest universe was born from a state that preserved or imprinted order across cosmic transitions. The more we learn, the more the Big Bang feels less like an absolute beginning and more like a continuation of something deeper, something encoded in the universe's earliest behavior. Scientists using quantum simulations have discovered hints of pre-Big Bang structure in the patterns of primordial gravitational waves, waves that might have been generated before the universe entered its explosive expansion. These waves, if confirmed, would be direct evidence of physics beyond the Big Bang, a whisper from a time outside the timeline we know. Some researchers have even proposed that dark energy, the mysterious force accelerating the expansion of the universe, may be linked to remnants of a phase transition predating the Big Bang. If true, the accelerating expansion would be a fossil of an older universe, still echoing through ours. All of this evidence, from background radiation to black holes to early galaxies, converges onto a single, profound question. Is the Big Bang just one chapter in a much older cosmic story? What we are discovering is not chaos but pattern. Not noise but signal. Not randomness but history. These clues do not destroy the Big Bang model, they enrich it. They stretch it. They press its edges until they reveal something larger hiding beyond. They tell us the universe is trying to speak. Trying to reveal where it truly came from. Trying to show that the moment we call the beginning may not be the beginning at all. Imagine the possibility that the cosmos carries imprints from before time, encoded in the oldest light, in the deepest voids, in the faintest gravitational ripples. That the universe we inhabit is not an isolated miracle but a descendant of something older, a sequel in a cosmic series stretching beyond imagination. And now, as new evidence accumulates, the curtain trembles. A crack appears. A faint glow leaks through from the realm beyond the Big Bang. It leaves us with a question that feels like standing on the threshold of discovery. If the Big Bang was not the first moment, then what ancient story is waiting on the other side, ready to be uncovered? Imagine the universe as a story written across the darkness of space, a tale filled with violence, beauty, collapse, and rebirth. For most of human history, we thought we understood the opening chapter. A fiery beginning, a cosmic dawn, a singular moment when everything burst into existence. But now, as evidence accumulates and theories evolve, those first pages begin to blur, revealing the faint outline of something deeper. As if the universe is urging us to reconsider, to rewrite, to expand our understanding of how everything began. And gradually, a new cosmic origin story begins to emerge, one far more intricate, far more ancient, and far more astonishing than the narrative we once believed. Picture the old story, a universe born from nothing, exploding outward, cooling and forming stars, galaxies and planets. A clean, sharp beginning. A neat explanation. A cosmic spark that ignited reality. But this picture now feels incomplete, like a reconstruction missing crucial fragments. The Big Bang remains a central event, but not the first event. Not the whole story. Instead, it is the middle of a much larger arc, the visible flare of a process that may stretch far into the past and far into the future. The new cosmic origin story is not a single theory but a convergence, a weaving together of clues, models, and mysteries. Each thread tells part of the tale. One thread points to a universe that existed before ours. A universe that may have collapsed into extreme density, smoothed itself through gravitational contraction, and then rebounded, not into destruction but into creation. The Big Bang becomes the bounce, the transition from one era to the next. Our universe becomes the child of a previous one, inheriting structure, entropy, and quantum information from its predecessor. Another thread reveals universes as bubbles in a vast multiversal ocean. Our bubble formed not from nothingness, but from a quantum fluctuation or a higher dimensional collision. The Big Bang, in this view, is the moment our cosmic bubble inflated and separated from a larger reality. The forces and particles that make our universe unique were shaped not by randomness, but by conditions inside this bubble, influenced by what came before or outside it. Another thread emerges from the mathematics of timelessness. In this model, the universe didn't begin. It simply transitioned from a phase where time had no structure into a phase where time crystallized. Before the Big Bang, there was no before because time itself had not yet formed. The Big Bang becomes not the beginning of existence but the beginning of time as we know it. Other threads come from the hidden architecture of spacetime, the idea that spacetime itself emerges from quantum entanglement, from patterns of information deeper than geometry. In this view, the universe began when these patterns achieved a stable configuration, when information condensed into space. The Big Bang becomes the moment spacetime switched from possibility to structure. Individually, each thread challenges the old narrative. But woven together, they form an origin story more coherent, more elegant, and more cosmic than the one we inherited. In this new story, the universe did not appear from nothing. It emerged from something, a prior state, a deeper layer, a timeless phase, or a higher dimensional landscape. The Big Bang is not a creation moment. It is a transformation, a boundary between eras, a shift in cosmic conditions. The laws of physics are not arbitrary. They are shaped by deeper rules that transcend our universe, influenced by previous cycles or broader realities. Time does not start at the Big Bang. It becomes meaningful at the Big Bang. The cosmos is not a lone miracle. It is part of an ancient, interconnected lineage of universes. In earlier centuries, the universe was thought to be static, then expanding, then accelerating. Now, perhaps cyclic or emergent. Each revolution brought us closer to understanding, but each also revealed how much we have yet to uncover. As this new origin story expands, it reframes everything about existence. It suggests that the universe is not fragile. It is resilient. It has survived transitions, bounces, collapses, and births. It has persisted across scales and dimensions we are only beginning to imagine. And we, tiny beings on a small planet, are part of that continuity. This story also deepens the emotional landscape of cosmology. Instead of a single miraculous beginning, we inherit a universe with history, ancient, complex, layered. A universe shaped by events that occurred long before stars ignited. A universe carrying the faint aroma of past worlds, past cycles, past realities. And what lies ahead? If the universe emerged from a prior state, then one day it may transition again. Our cosmic era may be one note in an infinite symphony. The expansion we see today may flatten into stillness, collapse into renewal, or stretch into another form entirely. The universe is not static. It is evolving. And we are living inside one of its transformations. The old story ends with a beginning. The new story ends with a horizon, a doorway, an invitation. An invitation to imagine a universe far older than time. An invitation to explore realities beyond our cosmic bubble. An invitation to see the Big Bang not as the spark that created everything, but as the moment our chapter began. And as this new cosmic origin story unfolds, one truth becomes clear. The universe is not a simple tale. It is an epic, still being written. Imagine the universe as a book without a first page. A story that seems to begin wherever you open it, yet always hints that something came before. Every chapter feels complete, but none reveals the true origin. As you turn the pages, you realize the narrative is not linear. It branches, loops, echoes. The deeper you read, the clearer it becomes. The universe is not a tale with a beginning and an end, but a vast, unfolding epic whose timeline stretches far beyond human imagination. Standing beneath the night sky, it's easy to believe you're witnessing the story from its opening scene. The stars shimmer like cosmic punctuation marks, the galaxies swirl like paragraphs, the cosmic microwave background glows like an ancient preface. But modern cosmology is beginning to whisper something more profound, that the universe may not have started with the Big Bang, and it may never truly end. Instead, it may exist in a continuum where the concept of a first moment dissolves entirely. Imagine walking through a library of universes. Each one is a volume in an infinite collection. Some books are thick with complexity, filled with galaxies, stars, black holes, and life. Others are thin, quiet, sparse. Each book tells a self-contained story, but none claims to be the first. You search for the beginning of the shelf, the starting point of the grand collection, only to discover that the library circles back on itself. No matter which direction you walk, the shelves keep going. This is the universe, a story without a first page. Consider the possibility that our universe is one cycle in a cosmic sequence. Before our expansion, another universe may have collapsed, condensed, and handed off information to the next cycle through a bounce. Our cosmos may carry the faint imprint of its predecessor, in the pattern of galaxies, in the structure of cosmic background radiation, in the subtle alignments that stretch across billions of light years. These imprints are not the beginnings of our story, but the whisper of another. Now imagine a different possibility, that our universe is a bubble in an endless cosmic sea, one bubble among countless others emerging from a deeper quantum landscape. Each bubble expands, evolves, and cools, but none is the first. The multiverse does not begin. It simply exists, endlessly spawning new universes the way a stormy ocean constantly forms new waves. In this version of reality, the Big Bang is nothing more than the moment our bubble inflated, not the birth of everything but the beginning of our local chapter. Then consider the idea that time itself may not be fundamental. If time is emergent, arising only when the universe takes on a certain structure, then the concept of before loses meaning. The Big Bang becomes a phase transition, not a starting point. In a timeless state, the universe may have existed without sequence, without cause, without duration, a raw potential waiting for structure to crystallize into what we call spacetime. Our entire sense of beginning may simply be the moment when time became meaningful to beings like us. Each of these visions offers a different doorway into the same stunning possibility. The universe is larger, older, and more mysterious than any single origin story can capture. And yet, within this vastness, our lives gain new significance. Imagine zooming in from the grand cosmic expanse to a single human face, yours. You exist inside a universe that may have no first page, but your own story does. Your life begins, unfolds, and ends. You feel the passage of time, the arc of existence, the desire for meaning. You are a finite being inside an infinite reality, searching for understanding. The contrast is overwhelming. The universe is eternal. We are momentary. The universe is vast. We are small. The universe does not need beginnings. We depend on them. And yet, this very contrast gives our presence extraordinary weight. If the universe is a story without a first page, then each moment we live becomes part of a narrative far older and grander than ourselves. Our actions, our choices, our ability to reflect on the cosmos weave us into the epic. We are not observers standing outside the story, we are characters written into its fabric. The atoms in our bodies were forged in stars, shaped by forces born from cosmic transitions, influenced by physics older than time itself. We are not separate from the universe's story, we are the latest sentence in it. Now picture the final moments of a human life. Time slows. Breath softens. The world narrows. In the traditional view, everything moves toward an ending. But in the cosmic view, endings are illusions, transformations, transitions. Just as the universe's beginning is a transformation instead of an origin. When a star dies, it becomes the seed of new stars. When a galaxy collides with another, it forms a new structure. When a universe ends, it may give rise to another. Every ending is a doorway. Every ending is a beginning disguised. So too with existence. As you reflect on this, a powerful idea emerges. The meaning of our lives is not diminished by the universe's endlessness. It is amplified by it. Our brief time here becomes a spark of awareness in a cosmos that may have existed for eternity. Our ability to question, to wonder, to imagine becomes an act of cosmic significance. We are the universe thinking about itself. We are the cosmos awakening to its own mystery. A universe without a first page is not a story without meaning. It is a story that invites meaning at every turn. And so the journey ends where it began, gazing into the night, contemplating the origin of everything, realizing that the question itself may be flawed. The universe is not a tale with a clean opening scene. It is an endless, evolving symphony, with movements before and after the one we are living through now. We stand in the middle of an infinite story, not at the beginning, not at the end, but at a moment rich with mystery, possibility, and beauty. And as you breathe in the cold night air, one truth rises from the depths of existence. The universe may not have a first page, but your story within it is entirely your own. Imagine drifting outward through the cosmos until every galaxy fades into a faint shimmer. The entire observable universe shrinks to a single glowing sphere suspended in an endless void. From this perspective, the truth becomes clear. What we call an ending is only a shift, a transformation waiting to happen. The universe is still writing itself, still unfolding, still evolving far beyond our imagination. Scientists once believed the universe would follow a single path toward its fate. Now, the possibilities branch like cosmic rivers. One future imagines an endless expansion, galaxies drifting apart until their light can never reach each other. Stars burn out. Black holes evaporate. Space grows colder and quieter, yet even in this darkness, new universes might bud from quantum seeds. Creation does not stop, it simply moves to new ground. Another possibility imagines the universe slowing, reversing course, and collapsing inward. Galaxies fall together. Matter compresses. Temperatures rise. The cosmos tightens into an ultra-dense state, not a death but a transition point, before rebounding into a new expansion. In this view, universes are born and reborn in eternal cycles, each one inheriting the echoes of the one before. Or perhaps the future will be stranger still, expansion accelerating until space-time itself tears, only for isolated pockets of stability to ignite new realities. Even destruction becomes creation. In every version, one idea remains. The universe does not truly end. It changes form. It evolves. It becomes something new. And in this vast future, consciousness, whether human or something beyond us, may continue the search. The universe may not grant final answers, but it offers an endless horizon of discovery. In a cosmos without a first page, there can be no final one. The story continues and we remain part of its unfolding.